Hello students. Today we are going to discuss alkynes, preparation and properties. What are called alkynes? Alkynes are the unsaturated hydrocarbons containing at least one carbon-carbon triple bond. Alk plus ine gives rise to alkyne. YNE, ine, indicates the presence of triple bond. So, the unsaturated hydrocarbons are classified into two types. They are alkenes and alkynes. Previously, we studied about alkenes, preparation and properties. Today, we are going to discuss preparation and properties of alkynes. Methods of preparation of alkynes and properties of alkynes resemble with alkenes. Let us see the introduction of alkynes. Alkynes contain a triple bond. The general formula of alkynes is CnH2n minus 2, where n represents the number of carbon atoms. If n is equal to 1, we never get any alkyne. If n is equal to 2, it is C2H2, ethyne or acetylene. If n is equal to 3, it is C3H4, propyne or methyl acetylene, and so on. So the first stable member of alkynes is acetylene. Therefore, alkynes are also called acetylides. Two elements of unsaturation for each triple bond. Two elements of unsaturation for each triple bond. Some reactions are like alkenes, addition and oxidation. Addition reactions which occur in alkynes resemble those which occur in alkenes. Similarly, oxidation reactions which occur in alkynes are also similar to those reactions which occur in alkenes. Some reactions are specific to alkynes. Now let us see the nomenclature. IUPAC, nomenclature of alkynes. Find the longest chain containing the triple bond. It is the first point. We shall have to find the longest continuous chain in the triple bond containing the triple bond. Numbering must be done from the side where triple bond is located. Change ANE ending to YNE ine. Number the chain starting at the end closest to the triple bond. Give branches or other substituents a number to locate their position. Look at the examples for the nomenclature, IUPAC nomenclature. CH3 bond, C triple bond, CH. Its common name is methyl acetylene. Methyl acetylene. But the IUPAC name of this compound is propyne. Since 3 carbon atoms are present, the root word is prop. Since triple bond is present, the suffix is ine, prop plus ine, propyne. Second example, CH3 bond, C triple bond, C bond, CH2 bond, CH2 bond, Br. Here, two function groups are there. One is Br, another is carbon-carbon triple bond. But carbon-carbon triple bond must be given the preference. So numbering must be done from left to right only. When we give the numbering from left to right, second carbon gets triple bond, fifth carbon gets bromine. Therefore, according to alphabetical order, bromo comes first. Therefore, 5-bromo 2-pentyne or 5-bromo pent 2-ine is the IUPAC name of this compound. Similarly, one more example, CH3 bond CH bond CH3 bond CH2 bond C triple bond C bond CH bond CH3 CH3. IUPAC name of this compound is 2,6 dimethyl 3-heptine. Numbering must be done from right to left only. So when we give the numbering from right to left, third carbon gets a carbon-carbon triple bond, second carbon has got methyl group, sixth carbon has also got methyl group. Since two methyl groups are present and two methyl groups are present, therefore dimethyl 2,6 dimethyl 3-heptine or 2,6 dimethyl hept 3-ine. Some more examples for IUPAC nomenclature. CH2 double bond CH bond CH2 bond CH bond CH3 bond C triple bond CH. In this case, double bond is present on first carbon. Double bond is present at the first carbon. Here, this chain contains both alkene function group and alkyne function group. Preference must be given while giving numbering. Preference must be given to the alkene. Therefore, numbering must be done from left to right only. Fourth carbon has got methyl group. Therefore, 4-methyl 1-hexene 5-ine. 4-methyl 1-hexene 5-ine. One more example, CH3 bond C triple bond C bond CH2 bond C HOH CH3. Here triple bond is there, therefore numbering must be done. Alcoholic function group is present. Whenever alcoholic function group is present as a substituent, numbering must be done from the side where substituent is like alcohol is present. That's why numbering must be done from right to left only. OH group is present on second carbon and triple bond is present on the fourth carbon. Totally chain contains 6 carbon atoms, 4-hexene 2-ol. 4-hexene 2-ol is the IUPAC name of this compound. Common names named as substituted acetylene. Example, CH3 bond C triple bond CH. This is methyl acetylene. Common name is methyl acetylene. Second example, isobutyl isopropyl acetylene. Isobutyl isopropyl acetylene. Since in alphabetical order, B comes before P, therefore isobutyl isopropyl acetylene. Now come to the physical properties of alkenes. Alkenes are non-polar in nature and alkenes are insoluble in water. Alkenes are soluble in most organic solvents. Boiling points of alkynes similar to alkanes of same size. Alkynes are less dense than water, up to 4 carbons gas at room temperature. Alkynes up to 4 carbon atoms are gases at room temperature. Means ethine, propane, butane are gases at room temperature. Acetylene gas is used in welding torches. In pure oxygen, temperature of oxyacetylene torch will be 2800 degrees centigrade. Acetylene is a combustible gas. When acetylene burns in oxygen, produces oxyacetylene torch. This torch is used for welding of railway track. The temperature of oxyacetylene torch will be nearly 3000 degrees centigrade. It would violently decompose to its elements. But the cylinder on the torch contains crushed fire brick wet with acetone to moderate it. Now come to the synthesis of acetylene. Acetylene gas is prepared in a laboratory by the hydrolysis of calcium carbide. Calcium carbide upon hydrolysis gives acetylene. This is the laboratory method to prepare acetylene gas. In order to prepare calcium carbide, we must adopt the equation. Coke reacting with lime gives calcium carbide. C plus CaO gives rise to CaC2 plus CO. CaC2 plus 2H2O gives rise to H bond C triple bond C bond H plus CaOH taken twice. Heat coke with lime in an electric furnace to form calcium carbide. When coke is heated with quicklime, that is CaO, in an electric furnace gives calcium carbide. This calcium carbide on hydrolysis gives acetylene. So this reaction was used to produce light for miners' lamps and for the preparation of acetylene gas. If you look at the electronic structure, the triple bond contains 1 sigma 2 pi bonds. The sigma bond is sp-sp overlap. The sigma sp-sp bond is formed by the head-on overlapping between sp hybrid orbital of one carbon atom and sp hybrid orbital of another carbon atom. The 2 pi bonds are unhybridized. P overlaps at 90 degrees, which blend into a cylindrical shape. The 2 pi bonds are unhybridized. The two unhybridized p orbitals of two carbon atoms overlap laterally and form 2 pi bonds. So, the resulting triple bond between two carbon atoms contain 1 sigma sp-sp bond and 2 pi pp bonds. When we observe the bond length values in ethane, and ethine, one thing is clear. Carbon-carbon single bond length in ethane is 1.54 angstrom. Carbon-carbon double bond length in ethene is 1.33 angstrom. Carbon-carbon triple bond length in ethine is 1.20 angstrom. As the number of bonds between two carbon atoms increases, the bond length decreases. More S character, so shorter bond length. In case of carbon-carbon single bond, S character is very less, whereas in ethene 33% S character will be found. In ethane 25% S character. In ethene 33.33% S character, whereas in ethine 50% S character. As the S character increases, bond length decreases due to the shortening of bond length, due to the coming close to each other. As the number of bonds between two atoms increases, the bond length decreases. Otherwise, as the S character of hybrid orbitals increases, bond length decreases. 3 bonding overlaps, so shorter. Bond angle is 180 degrees, so linear geometry. In acetylene molecule or in ethyne molecule, bond angle is 180 degrees, therefore the shape of ethyne molecule is linear. Acidity of alkynes. Alkynes are acidic in nature. The two hydrogen atoms present in a molecule of alkyne are acidic in nature, therefore they are also called acidic hydrogens. Terminal alkynes R bond C triple bond C bond H are more acidic than other hydrocarbons. Acetylene gives acetylide by NH2 but not by OH minus or RO minus. Acetylene gives acetylide by NH2 minus but not by OH minus or RO minus. More S character, so pair of electrons in an ion is held more closely to the nucleus, less charge separation, so more stable. If you look at the table, compound, conjugate base, hybridization, S character, and pKa values. Ethane, ethene, and ethyne. Type of hybridization: sp3, sp2, sp. S character 25%, 33%, and 50%. pKa values 50, 44, and 25. pKa is equal to minus log Ka. So, greater the value of pKa, lower will be the acidic character. So, ethane has higher pKa value, therefore ethane is weakly acidic in nature. Since ethyne has lower pKa value, therefore it is strongly acidic in nature. Forming acetylide ions. Hydrogen can be removed from a terminal alkyne by sodium amide NaNH2. When propyne reacts with soda amide, gives methyl acetylide, sodium methyl acetylide, and ammonia. NaNH2 is produced by the reaction of ammonia with sodium metal. When ammonia reacts with sodium metal in the presence of ferric ion, gives soda amide NaNH2, which contains Na plus and NH2 minus. Heavy metal acetylides. Terminal alkynes form a precipitate with silver 1 or copper 1 salts. Terminal alkynes form a precipitate with silver salts and copper salts. Internal alkynes do not react. Internal alkynes do not react. 2 uses: qualitative test for terminal alkyne, separation of a mixture of terminal and internal alkynes. Now let us discuss the qualitative test. Reagent is AgNO3 or CuNO3 in alcohol, silver nitrate or copper nitrate in alcohol, or ammonia is added to form the complex ion. The solid is explosive when dry. Copper tubing is not used with acetylene. See, when methylacetylene is treated with cuprous oxide, when methylacetylene or propine is treated with cuprous oxide, the hydrogen atom of propine is substituted by cuprous ion. This reaction shows the acidic nature of propine. Formation of heavy metal acetylide indicates the acidic property of alkynes. Synthesis by elimination. Removal of two molecules of HX from a vicinal or geminal dihalide produces an alkyne. Preparation of alkyne. First step, minus HX is easy. First step is minus HX. Elimination of hydrogen halide forms vinyl halide. Second step, removal of hydrogen halide from the vinyl halide requires very strong base and high temperatures. When we observe the equation, 2,3-dibromopentane, 2,3-dibromopentane on treating with fused potassium hydroxide at about 200 degrees centigrade gives 2-pentyne, molten KOH or alcoholic KOH at 200 degrees centigrade favors an internal alkyne. Here dehydrohalogenation takes place. Dehydrohalogenation. During the process of dehydrohalogenation, removal of two hydrogen halide molecule takes place. Removal of two hydrogen halide molecules takes place. Alcoholic KOH or fused KOH. Alcoholic KOH is called dehydrohalogenating agent. So 1,2-dibromopentane upon heating with alcoholic KOH gives 1-pentyne or pen to 1-ine. 2-pentyne or pent to 2-ine. Sodamide or sodium amide NaNH2 at 150 degrees centigrade followed by water favors a terminal alkyne. CH3 bond CH2 bond CH2 bond CHCl2 upon heating with a sodamide at 150 degrees centigrade gives a terminal alkyne, that is 1-butyne. Addition reactions. Addition reactions occur in alkynes. Why? Because alkynes are the unsaturated hydrocarbons. These addition reactions are similar to those addition reactions which occur in alkenes. Pi bond becomes 2 sigma bonds. Usually the addition reactions are exothermic. One or two molecules may add. In this table, as the number of bonds between two carbon atoms increases, bond energy also increases. Addition of hydrogen. Three reactions. Add lots of hydrogen with metal catalyst, palladium, platinum or nickel to reduce alkyne to alkane, completely saturated. Use a special catalyst, Lindlar's catalyst, to convert an alkyne to a cis-alkene. React the alkyne with sodium in liquid ammonia to form a trans-alkene. Anyhow, by the addition of hydrogen using a special catalyst, we can get cis-alkene and trans-alkene. Cis-alkene is obtained from alkyne using Lindlar's catalyst. Trans-alkene is obtained from alkyne using sodium in liquid ammonia. Lindlar's catalyst. Powdered barium sulfate coated with palladium. Powdered barium sulfate coated with palladium. Poisoned with phenolene. Hydrogen adds, so cis-alkene is formed. Addition of halogens. Addition of halogens. Cl2 and Br2 add two alkynes to form vinyl dihalides. When Cl2 or Br2 are added, we get vinyl dihalides. May add syn or anti, so product is mixture of cis and trans isomers. Difficult to stop the reaction at dihalide. Look at the reaction. This is methyl acetylene, CH3 bond, C triple bond, C bond H. This methyl acetylene or propyne reacts with hydrogen bromide. Dehydrohalogenation. In this reaction, addition of HX takes place. Addition of HX, according to Markovnikov's rule, negative part of the reagent is added to the carbon containing less number of hydrogens. Therefore, Br is added to the second carbon atom. Now, 2-bromopropene is obtained. In the first step, this 2-bromopropene further reacts with HBr, giving rise to 2,2-dibromopropane. 2,2-dibromopropane. One thing you remember, addition reactions which occur in alkynes involve two steps. In the first step, triple bond is converted into double bond, whereas in the second step, double bond is converted into single bond. Therefore, totally two molecules of the reagent are involved in the addition reaction. HBr with peroxide. HBr with peroxide. In the presence of peroxides, anti-Markovnikov product will be formed. Anti-Markovnikov product is formed with a terminal alkyne. Propyne is a terminal alkyne. This propyne reacts with HBr in the presence of peroxide, gives an unstable product, that is alkene, gives an alkene. This alkene further reacts with a molecule of HBr, giving rise to an alkane. Ultimately, we get 1,1-dibromopropane. 1,1-dibromopropane is the final product of the reaction. In this one, anti-Markovnikov rule is followed. So in the presence of peroxide, HBr, addition of HBr takes place according to anti-Markovnikov rule. Hydration of alkynes. Hydration means addition of water. Mercuric sulfate in aqueous sulfuric acid adds water molecule to 1 pi bond with a Markovnikov orientation, forming a vinyl alcohol that rearranges to a ketone. Remember, when an alkene is passed into water in the presence of HgSO4 and sulfuric acid, forms vinyl alcohol, that is unsaturated alcohol. This vinyl alcohol undergoes rearrangement to give a stable compound, that is ketone. If you observe the reaction with acetylene, when acetylene gas is passed into sulfuric acid, dilute sulfuric acid, in the presence of HgSO4, that is mercuric sulfate, gives vinyl alcohol. This vinyl alcohol is an unstable compound. Immediately, it undergoes rearrangement, giving rise to a stable product, that is acetaldehyde. Hydroboration, oxidation adds water with an anti-Markovnikov orientation and rearranges to an aldehyde. Oxidation of alkynes. Oxidation of alkynes is similar to oxidation of alkenes. Dilute neutral solution of KMnO4 oxidizes alkynes to a diketone. Warm basic KMnO4 cleaves the triple bond. Ozonolysis followed by hydrolysis cleaves the triple bond. So oxidation process occurs in alkynes. The oxidation process which occurs in alkynes is similar to the oxidation process which occurs in alkenes. Ozonolysis. Ozonolysis, already we studied about ozonolysis in alkenes. Ozonolysis is a test to detect the unsaturation. Ozonolysis helps us to know the presence of carbon-carbon double bond or carbon-carbon triple bond. This ozonolysis is used to detect the unsaturation present in a given compound. Ozonolysis of alkynes produces carboxylic acids. Alkenes gave aldehydes and ketones. In previous class, we studied ozonolysis of alkenes. Alkenes react with ozone, giving rise to alkene ozonide. This alkene ozonide is unstable compound, undergoes hydrolysis in the presence of zinc, giving rise to carbonyl compounds. Here also same thing. Alkynes react with ozone, giving rise to alkyne ozonide. Alkyne ozonides undergo hydrolysis in the presence of zinc, giving rise to ketones, giving rise to carboxylic acids. Example, 2-pentyne. Ozonolysis of 2-pentyne. 2-pentyne undergoes ozonolysis. During the process of ozonolysis, ultimately we get ethanoic acid and propanoic acid. Means acetic acid and propionic acid are obtained as a products of ozonolysis. This ozonolysis is useful to find the location of triple bond in an unknown compound. So, the addition reactions which occur in alkenes are also similar which occur in alkynes. Addition of hydrogen, addition of halogens, addition of hydrogen halide, addition of water, ozonolysis. One more thing, polymerization. Already we discussed about polymerization of alkenes. Alkenes undergo polymerization. When ethene undergoes polymerization gives polyethene. Similarly, alkynes also undergo polymerization. Two or more number of small molecules of a compound combine themselves to form a large molecule is called polymerization. When acetylene gas is passed through a hot tube at high temperature, when acetylene gas is passed through copper tube at high temperature at about 600 degrees centigrade, three molecules of acetylene polymerizes to give benzene. We can write the equation 3C2H2. 3C2H2 gives rise to C6H6. When acetylene is polymerized, ultimately we get benzene. So, polymerization reaction, which is possible in alkenes, it is also possible in alkynes. Oxidation reactions, which occur in alkenes, also occur in alkynes. If we compare the reactivity, already we studied that alkenes are more reactive than corresponding alkanes. Why alkenes are more reactive than corresponding alkanes? Because of the presence of pi bonds. Pi bonds are found in alkenes. Pi bond is a weaker bond than a sigma bond. Alkanes do not contain pi bonds. Alkenes contain pi bonds. The pi bonds are responsible for the high reactivity of alkenes. When compared to alkynes, alkynes are less reactive than corresponding alkenes. The question arises why alkynes are less reactive than corresponding alkenes. Because of the shorter bond length in alkynes. The bond length in alkynes is lower than the bond length in alkenes. 1.34 angstrom is the bond length in alkenes. Carbon-carbon double bond length is 1.34 angstrom, whereas carbon-carbon triple bond length is 1.20 angstrom. So due to the shorter bond length, the mobility of pi electrons will be less. Due to the less mobility of pi electrons in alkynes, alkynes are comparatively lower reactive or less reactive than corresponding alkenes. It means that ethyne is less reactive than ethene. Similarly, propyne is less reactive than propene. Butane is less reactive than butene. So all alkynes are comparatively less reactive than corresponding alkenes. Thank you.